Now my second order approximation is going to be a little bit different. It's going to be the linear term plus a quadratic. Okay, so the reason we have this half here is because if you take the second order derivative of this function with respect to delta t, what do you get? Yeah, if you take a first order derivative, you get a half. Sorry, when you take a first order derivative, you cancel the half, right? You get d squared u dt squared times delta t. And then you take a second order, you take a derivative again, right? The delta t goes away, you get this. So basically, the half goes away when you take the second order derivative, which means this term actually have a second order derivative that coincides with the second order derivative of u. What you're doing is I'm going to add a quadratic so that the second order derivative actually is going to coincide with this original function, right? Okay, so that's my second order approximation. And I'm going to add, it's actually a third order approximation. And the third order approximation is going to be proportional to delta t cubed by definition, right? And we also want to make the third order derivative to match. So we have a third order derivative. And what constant do I need to multiply here in order for the third order derivative to match? 1/6, right? Because when you're taking derivative of this, the first time you get a 3, the second time you get a 2, right? So you have 6, so 1/6. And then it'll follow, right? You add arbitrarily many terms, and for the, let's say, kth term, it's going to be delta t to the kth power, and here you have a kth order derivative of u. And here you try to match the kth order derivative, right? So if you take a derivative k times, you get a k, you get a k minus 1, you get k minus 2, etc. So you get k factorial, right? In order to match, you have to have 1 over k factorial. So this is basically a review of Taylor series. So why is it useful here? It is useful here because if you plug in this Taylor series into here, okay, do you see something coming out? You see this term cancels with this term, right? So the constant term is gone. All right? Okay? And then the first order derivative term is not cancelled, but the delta t is cancelled, right? The delta t is cancelled. So we just get the first order derivative, which is exactly what we want to approximate. All right, so constant term gets cancelled out. The first order term becomes exactly what we want to approximate. And all the rest contributes to the approximation error. Just by looking at the effect of all the rest, we can do analysis of what the approximation error is. Now let me remind you that we don't want the approximation error for arbitrary delta t. We want the approximation error when delta t is very small. Okay, so by looking at all the rest, which is starting from the term that is a second order, which term do you think is the most important when delta t is very small? Yeah, so this term is going to be most important because when delta t is very small, anything that is delta t, every time you multiply by delta t, you make things even smaller, right? So the most important term is going to be the term that's multiplied by delta t the least amount of time, which is going to be the second order term. So in Taylor series analysis, if you are smart, you are not going to be carrying out all the terms. You are only going to be carrying out just enough terms such that you only get one term that is not cancelled. Okay, if you cancel up everything, you get 0 error, right? I mean, which means you didn't get the error, right? But if you have one term that ended up not cancelled, that is going to give you how much the error is when delta t is very small. Okay, I'm going to